because this unitary system only supports one control zone. But how can we do that? As I mentioned, the air loop is basically we disassemble this system and then build each component one by one. We can do that. That means we can directly use merge component to connect the heating coil and the fan to the supply side of the air loop. We okay. Let's just copy. Let me do Control Z, Control Z, Control Z, Control Z, and let's copy everything as a new system. This is a new system, and we don't need the air loop unitary system. In this case, we use this heating coil, cooling coil directly. Use a merge, so all air flows go through the heating coil first, and then the fan, and to the supply side. Now, what about the supply air temperature? How can we control that? We can use. Let's go to the Ironbug. So we have to introduce a new component called the setpoint manager. What it does is basically sets a value for a loop. It can be the air loop or plan loop based on a certain threshold. Let's say for this case, let's use the simplest one, the setpoint manager scheduled. That means because this object parameter is for a unitary system, we cannot use that one. We just use the same 60. In this case, a variable to 60, and the control variable is temperature. Temperature. Big. That means we want the airflow after the fan to be the 60 at this point. So air flows from heating coil to the fan to this setpoint manager, and this one basically controls what's the temperature you want to supply air at. Now let's try to run the system. Let me check the supply side. So we have three items at the supply side. One is a cooling coil, a heating coil, a fan, and the scheduled setpoint manager. I see here the fan is still named as a zone equipment fan, but which is not correct anymore. I'm going to delete this guy. And if you use a template, there is fan system model VAV. Oh, Control Z. This guy, I'm going to use this default setting for this fan. Replace. Okay. Now the fan is a VAV. It has other parameters updated as well based on the fan for the air loop variable control. Okay, and everything the same. Let's try to run a simulation with this new system. The HVAC system. Control S, save the file, run. Now, if you look at the value output here is equal a the heating is like close to 200. It's way much higher than previous one, previous setting. So why is that? So first of all, let's check the unmet hour first. See if all looms operating correctly. You can see all looms are fine now. That's good news. And our energy use is way much higher than the previous one. Now let's look at do we have other inputs? No. Let's look at the system. What can we do? Let's check the heating. Heating is way much higher than the previous one. Let's request heating core electricity energy. Yeah, we did. Heating core electricity energy. Heating coil. And the fan. Okay. Because we already ran the simulation with this output. The heating coil electric energy for the heating coil and the fan electric energy for the fan. So we just want to look at the hourly data, see what if everything makes sense, and then we just combine the unmet hour variable and output variable with the heating coil electricity energy and the fan electricity energy, and then we just request those results from SQL file, and then we can just run. We can visualize that. Okay, the last two I believe is heating coil electricity and the fan. The fan seems it's all constant here, so it's fan is running through it's running every hour throughout the year. At the every hour is using 8.5 kilowatt hour, which makes sense why it's so high. The system is running always constantly running throughout the year. That's why even during the summertime, you can see the heating electric energy, the lowest point is 9.3. Even during the summertime, midtime, during the noon time, it's still running the heating. That's probably there's some issue with, let me turn off the simulation here. There's something issue with setpoint manager, how it controls the system to run the heating coil and the fan. Let's check what other setpoint manager we have from the list. We can see probably we can try to use here a setpoint manager multi-zone heating average. So this one basically evaluates all zones from this Airloop and try to run the system based on this input threshold. So minimum setpoint temperature and the maximum setpoint temperature for heatings. We can read the description here, but I'm going to use replace the scheduled setpoint manager with the new settings here, and default is 20. So the minimum, I'll just keep that one as a 20 Celsius, and the maximum is 50. I'm going to use 60 here. Let's run the simulation again, see if it helps. Alright, it seems the good news is the total value is going down 110 and heating is almost no heating at all 0.8. And let's check unmet hour and other values. So for the heatings unmet hour, it's all fine. There's no uncomfortable hours. That looks fine. That's good news. And the heating energy, yeah, that looks fine because zero, the dark blue is zero, and it barely turns on at for some hours during the morning time, and in some day it turns on throughout the day. And the fan seems still running every hour throughout of the year. That's why we are seeing the fan energy is so high because it never stops. We can now what we can do next. So what we are trying to do is because this system is only for the heating purpose, we only want a system running if the outdoor air is at a certain temperature. We want to turn off the system based on certain schedule. What we can do here is basically we can try to set up the availability schedules based on the room temperature. If let's say availability manager, let's use the availability manager high temperature turn off, and then we can. So what this availability manager does is whenever the input value of this probe higher than the setting, it turns off the system. The probe is we can just type in OB probe, node probe. So the probe and the parameter, let's use the object parameter. So the temperature, let's see if the room temperature is larger than 23 Celsius, we turn off the system. Does that make sense? Whenever indoor temperature is larger than 23, we turn off the system. So we can either turn off the fan or turn off the entire system. We can use as object parameter to the Airloop, and by default there's no availability scale manager as the input. We can right click parameters, availability managers, and set up availability manager. Now the question is where do we want to place this node probe? I think we can add it before the heating coil. So here, before the heating coil, where is this guy? So before the heating coil, because the first component we are adding to the Airloop supply side is a heating coil. So before the heating coil is basically all the return air from the terminal, from the thermal zone. So that means at the current state, it checks all air temperature first from the return air and use this one to control the entire air loop and turn off the system whenever the return air is higher than 23 Celsius degree, because we have this availability manager high temperature turned off here. Okay, and let's run the simulation, see if everything works. Now you see the fan is using way less the energy than the previous one. I guess we are turning off the fans during some hours. You can see the fans output fan electricity energy. The lowest point is 0, that means it's completely shut down during some hours. Even in the winter, the daytime, those hours are turned off. See? And only runs whenever the indoor temperature, the return air temperature is larger than 23 Celsius. Okay, check. And there's no unmet heating out hours. See, all rooms are fine. And until now, I can consider this system, this setting, this air loop works as expected. And we have checked unmet hour for all zones, and then we check each hour's data for the heating coil and the fans. Everything works expected. So I will complete this video here, and next one we will do a more complex system with hydraulic system. All right, thanks. Bye.